checking on the weather. I'm going to ramble about the subject of photovoltaics. You'll notice I'm rambling because it's not necessarily very coherent. It's a sort of a personal history. Now, interspersed with it, there are some genuine facts, and they should be recognizable as such. But, so what I propose to do is give you a little bit of background with photovoltaics, which started quite recently, like in 1800 and something. So it's nice to be doing modern technology. Anyway, and then to talk about very specifically how I got into the thing and what contribution the work that was done in our small lab on Route 128 in the Boston area made to the field, together with a few reminiscences of odd events that had occurred, obviously unscheduled because they were random. But anyway, the first slide, boink. This guy Becquerel, very famous scientist, he in fact discovered the photovoltaic effect in 1839. It's quite a while ago. More impressive to me in a way is that in 1883, this guy Fritz actually made a solar cell, not using silicon. I don't think anybody had actually seen elemental silicon back in those days. The only kind of silicon was the stuff you see in the form of an oxide when you run on the beach. But anyway, he built one out of selenium. Selenium is a kind of half-assed semiconductor. I don't think you really want. Though optical detectors made out of selenium were used for quite a long time. Now, this is the real big breakthrough. 1954, three guys, where else? Bell Labs, invented the silicon solar cell, which was a p-n junction device, which when illuminated produced direct current from the wires. Being Bell Labs and being the place where the transistor was invented, these guys are pretty thoroughly familiar with semiconductor technology, so it was no great strain for them to understand how this thing worked. But in fact, by sort of improvements they were able to make over a relatively small number of years, they got up to 10%. One of the people who worked with them is a guy called Morton Prince. Mort Prince is a good friend of mine who actually has an apartment in Jerusalem. I see him from time to time. This guy, a very interesting man, Paul Rappaport, was at RCA at the time. Very, very capable guy. And he and another very capable guy, Joseph Lafersky, were actually invited by the powers that be, whoever they are, to develop a solar cell for use as a power supply for space. To remind you, Sputnik worked on batteries. When the batteries were used up, the Sputnik stopped beeping. It still floated around and around and around a lot, but it didn't do anybody much good because it produced, but it could neither receive nor transmit signals. So these guys were actually asked to develop a solar cell for space, which makes a whole lot of sense if you can think about it, because you're a bit closer to the sun, there's no cloud cover. It's more reliable if you put the thing in the right orbit, you can get a lot of sunshine. And indeed, Vanguard 1, which in a certain sense was America's first answer to Sputnik, was indeed the very first space vehicle whose power supply was a solar cell. Or in fact, it was a group of solar cells, a solar panel. The fact that it produced less than a watt, I couldn't find this thing on the bloody typewriter which said less than, so I put approximately a watt. But it was actually quite a lot less than a watt, but it was enough to power a radio. And in fact, all the communications with this thing were done using photovoltaic power. And that's 1958. A little bit more history. 1982 was the first 1 megawatt solar array. I want you to notice, Amit, I'm pointing at somebody in the audience, that it used a dual-axis tracker. Now, normally when you think of solar cells, you see these flat things on roofs or raised. But if you actually move them around and follow the sun, especially in two axes, because the sun goes up and down as well as side to side, you can get about 40% more energy from the same amount of solar cells. So it's very well worth considering whether the complications involved in the moving parts and the tracker and whatnot are worth their weight in energy. We think they are, don't we? We still think so? Yes, we still. This was a sort of a milestone. I picked some of these out of some stuff that was very kindly sent to me by Yvonne. I mean, that's some sort of a benchmark. 1 gigawatt. 1 gigawatt, when you compare 1 gigawatt to the energy supply, even for a small country like Israel, it's absolute peanuts. But if you consider it compared to the less than a watt, and not that very many years before that, it's a milestone of some sort. Gigawatt. 2000 to 2010, I'm sparing you lots of graphs and stuff. But I'll simply say, like Topsy, this thing just grew and grew and grew and grew and grew, to the point where, and you may suspend belief if you like here, but these are verifiable facts. In the year 2010, there was $80 billion worth of photovoltaic systems, almost 95% of it based on silicon. $80 billion. You know, when people come in with startups and you say, well, what's the market for this thing? They say, well, you know, the market's actually $300 billion a year and we expect to get 10% of it. Here, we don't need to talk about the market. The market for early stage companies is essentially infinite. But not all the progress went in one direction. Just this very week, to the embarrassment of President Obama, a company called Solyndra, this was one where I guessed right. When I saw this thing, I think I said to you, this will never take off. This is a very clever idea. This was a tubular device with the solar cells on the inside, thin film solar cells, and you could roll them around and so forth. But anyway, they raised immense amounts of money, and I'm glad to say from some extremely well-known VCs in Silicon Valley who will always tell you the good things they've done, but don't talk very often about the stupid things they've done, and this is certainly one of them. But also the US government wasn't too bright either. They lent them over $500 million. And the company just declared bankruptcy last week or the week before. Normally when companies in our orbit go broke, you know, you're talking about tens of millions of dollars worst case. Here you're talking about billions. Okay, what's my story? How did this happen? I mentioned this guy, Paul Rappaport. He was at RCA, and he and I had been at a conference in Cherry Hill, New Jersey. Can't remember the year, and I couldn't find it. And it was about solar cells and alternate energy and whatnot, because the US military was very keen on developing portable power-producing systems. And one of the things you had to consider was solar cells. And Paul and I and two other guys, or one other guy, I'm not sure which, sat down together, and on the back of an envelope, there were no computers around by then, so it was quite a... We did a calculation which basically said that instead of the prices of space solar cells, which are measured in hundreds of dollars per peak watt, hundreds of dollars per peak watt. Now you don't get peak watts all the time, you know, the sun is not at its full strength for very long during the day. Here we had to get down to 50 cents a watt. That was my number. I pulled it not quite out of the air, but almost. 50 cents a watt. Actually, if you translate that, this was in the late 60s, if you translate that into today's dollars, it's not far off the right number. It's pretty much, I mean, if that wasn't good, I wouldn't be telling you the story. And if I'd been 2 orders of magnitude out, you'd never have heard of that. And we did this, and this is where I think, I was a crystal grower. When I did any science at all, which was as rarely as possible, it would usually have something to do with crystals or crystal growth or what have you. And also I was pretty good at christening techniques. So if you, I don't know about children, but if you want a catchphrase for your technology, you could do worse than ask me to see if I can come up with it. It's very obvious if you want to make cheap solar cells, you need silicon that's a hell of a lot cheaper than the stuff you grow for the semiconductor industry, which back then wasn't that big, but they're now 12-inch diameter crystals that weigh God knows what. And then you slice them up with saws, destroying about half the material in the process of producing slices. Then they're round rather than square, which isn't very good for density, for high density cells. So what you really need is, no, I think I've skipped, yeah, you go back this, I think I've skipped a few.
You skipped the drawing.
What? Can you go back?
Yeah.
Yeah, there you go. Is there one before that? No, okay. I will show this picture. This describes something called EFG. EFG is the name that I coined for a technique of crystal growth for edge-defined. If you look, here's the crystal of sapphire. Sapphire, so really aluminum oxide. Sapphire. The shape of the crystal is defined, if you notice, I don't know if you can see it at the back of the room, is defined by the outside edge of the die. This is not extrusion. This is not, you don't get the shape from the inside, you get from the outside. And it's grown from a thin film of molten material, which through the magic of physical chemistry and surface tension is automatically created and is pretty damn stable. So you can grow this thing, and if you think about it, if you can grow a ribbon, you can grow a tube. Whereas you have two concentric tubes with a space between them, which acts as the capillary to bring the molten material to the surface, you can grow a tube. In fact, I had a young man working for me. We grew most incredibly bizarre shapes. And quite a few of them are in the Smithsonian Museum, I might say. We had licensed a company called Kyocera before it was Kyocera, when it was called Kyoto Ceramics. And I took the liberty of borrowing this drawing from one of their publications. Because I don't have a drafting board in my office anymore. I used to have one in the old days. Now you can see what you need here. You've got to have a crucible which is chemically resistant to the stuff you're melting, which in the case of silicon is no mean job. You can use quartz. It's very difficult to machine quartz to the sort of dimensions you need to get this sort of accuracy. So you really need, and now I can go back to point, you need a precisely machinable material, chemically inert to molten silicon, which is something close to mission impossible, but my best guess was that graphite wouldn't be bad. Why not? Graphite, carbon is a group 4 element, silicon's a group 4 element. We get a bit of carbon in there along with the silicon atoms, asma. And the solid solubility of carbon in silicon is not very high anyway. And you can purify the hell out of graphite. I mean, you can get it at exceedingly high temperatures in the vacuum, and you can really get it very, very pure. So we tried carbon, and lo and behold, it worked. Based on a very crude sample which we produced, so crude that if I had a picture of it, I wouldn't show it to you. I'd leave it to your own imagination. Really, I went trotting off, and I decided, also on the back of an envelope, that what we needed was $50 million in about 10 years to go from that deformed piece of silicon to a process for producing solar cells at 50 cents a watt. And it's funny how I chose mobile, lucky people. I looked at Fortune 500 lists at the time. And number one at the time was ATT before they broke it up, and I thought it didn't sound very cool. GE was up there, and I thought this is an NIH thing big time, not in the country. They'll never, GE will never do it. So I said, oil companies. The Exxon, which was then called Esso, had already been stolen by a man who later became my friend. He was thought about solar cells as well, but he was thinking about compound semiconductors and thin film stuff. So I picked Mobil and I decided they would be the lucky people who would have the opportunity of investing $50 million. So based on a very long business plan, which was about a page and a half, I went into the headquarters of Mobil in New York, and I think I gave new depth to the feeling of the local spa. Because I walk in there, I'm not even sure if I had an appointment. I mean, I can't exactly remember if I did or not. But I walked in there and I simply told the receptionist I'd come to see the top man, and he was so taken aback that he called the top man. And he was so taken aback, he said, "You better send him up." So I go up there, and I unwrap this tortured bit of silicone, and I hand this guy this 1.5-page thing, the burden of which was, for a mere $50 million, $1969, it's a lot of money. A mere $50 million over a 10-year period, Mobil could produce a new source of energy which would give them a much better image than they were getting from the oil business. I think that was an important part of their decision to support this. And that's what I'm missing. Anyway, the guy said, "Sounds like too much. How about 30 million for 7 years?" So I said, "Okay." And I have to tell you, believe it or not, when you talk about the difficulty of doing business with large companies, it's a question of how you go about it. It was somewhat less than 8 weeks from the day that I walked into their office at 72nd Street in New York to the day where they were picking up the tab for all of our activities in the field, which was about 108 weeks. And the deal was, once they had invested $30 million, they would own 80% of a joint venture to be called Mobil Tyco Solar Energy Corporation, the ownership of which would later depend upon the relative contributions of Mobil and Tyco. It was very clear Tyco would never invest in this thing, but eventually it became Mobil Solar Energy Corporation. Anyway, that was sort of fun.
3 minutes.
Now, how much? 3 minutes, wow. You've all half. Anyway, how do you grow it? When we tried growing ribbons, we could do it. The trouble was the edges were pretty different from the middle. So I had one of these great ideas of why have edges? Why not have a closed shape? So the closed shape was in fact a polygon. To put this in context, the size of these things is about 125 millimeters. And we grew these thin-walled polygons. You can work out what the die looked like just from the first diagram I showed you. They were not difficult to make. I mean, graphite's beautifully machinable. You can do it with great accuracy. It's very stable. And in fact, and you can grow them as long as you like, because since the growth occurs up here, and the molten material is below this and brought there by a capillary reaction, you can actually dump silicon into the melt while you're growing it, so you can a continuous process, which is unheard of for normal crystal growth. Okay. In 1994, Mobil, having finally realized that not only did they not belong in this business, but they were basically incompetent to run it. I think it may have had something to do with the fact that I left them in 1979 for 2 years, and there was no longer anybody there as a real advocate to be an interface with the headquarters. Shot solar. I'll hurry along. And here's just some miscellaneous things. I won't dwell on them very long. David Feynman, those of you in the solar energy business have surely know who he is, and you've been to see him. When I went to see him, I got a real kick about the fact that the most efficient panel he'd ever measured at that time had been made by Mobil Tyco back in the 80s. It was 14+% efficient. Not bad. Here's the funny one. We formed a joint venture with 3 major Japanese companies, Kyocera, Sharp and Matsushita, Mobil and Tyco. That was a lot of fun. Mostly the fun was the ceremonies that were associated with it when we went to Japan, and the geishas and the big dinner parties and all this other stuff. There's still in existence Japan Solar Energy Corporation, but I don't think they use the technology that we licensed to them. And now, final thing, this one was a real surprise. My son-in-law comes to me a few weeks ago and he says, look, there's this deal you can get if he has a flat-roofed house in Haniel, which is on the Moshav, not far from Payona, not far from Matanya. And if you cover your roof with solar cells, you can sell the power to Chevron Kashmal. The bank will loan you the money. You don't have to do a bloody thing. Just provide them the roof. Provide them the roof, and with a bit of luck, it'll never cost you a nickel, because the sale of the money you get from selling electricity to the company to the electric company is more than the interest on the loan. So eventually you make some money. So anyway, why am I telling you this about my son-in-law? Well, believe me, this could not have been planned. And I said, just, oh, by the way, whose panels are you using? And he said, Schott Solar. I said, do you realize you are now, in 2011, about to do something which is based on something which your now father-in-law started doing back in about 1970. So I don't like this phrase, who said what goes around comes around. But if you're ever going to use it, this would be the case where you have to use it. And the last thing is just this. EFG, if you just look up EFG on Google, Google it. Google EFG, Google EFG crystals, Google EFG crystal growth. If you just Google EFG crystal, you get about 500,000 hits. I mean, the technique is called on. It's been used for growing a huge variety of materials. It's been used for growing a huge variety of constant cross-section crystals of all kinds. And it actually works out again. So the fact that Schott is competitive and can sell in competition with the Chinese and a lot of other companies, sell panels which are now over 18% efficiency at the panel level. I mean, you know, not just the cells, but the panel with all the stuff around the edges and whatnot. I think vindicates the fact that the secret is cheap silicon. And now raw silicon has come down in price so much that the silicon is no longer considered as a primary cost element in the silicon solar cell system. It's all the other stuff, like the wires they'll get up with and the things you perch it on. So there's an introduction to new energy things based upon something which was invented nearly 200 years ago. Thank you.
Thank you.